Hello and welcome to my Nintendo Entertainment System video on using VBCC compiler with the LazyNes lib. In this video, hopefully I will go over and explain how to actually use this. So first off, I'll explain, if you see my other videos, then I was using GBDK before. So one of the things that I found when I actually got an NES and I also purchased an N8 card was I was not able to actually use any of the GBDK built ROMs, and that's because of the mapper which GBDK outputs. It uses mapper 31 and 4 screen mirroring, which the N8 cards do not support. I believe some of the more expensive EverDrive cards do support the mapper 31. However, the price ranges for those are definitely out of my reach. So I decided to look at some of the other libraries for building NES ROMs, and I found the files that VBCC builds for us work on the N8 card and thus work on an NES. And the N8 cards are within the price scope of most people, I believe. So also with the GBDK files as well, there's no ability to change the name table configurations. If you've looked into the Nintendo, you'll see that it has like a horizontal screen mirroring, which is for vertical scrolling, and vertical screen mirroring, which is for horizontal scrolling. These are configs which the ROMs are set up to support, but there's no means to set those with GBDK because you need to be able to actually edit and change some of the header bytes in the ROM files themselves, which is not supported, or at least I've no idea how you would do that in GBDK. Anyway, in this video I'll show you how to create those ROM types and how we can edit some of the header bytes, and then I will show some means of creating some graphics and then setting up some scrolling and how to sort of use the LazyNes functions. So let's overview the LazyNes library here. So it's very similar to a library called NESLib, which is for CC65 C compiler. You might have looked into that already if you've previously considered coding for the NES. So both the LazyNes and the NESLib were written in 6502 assembly, and the interfaces, as in the functions they sort of give, are very minimal. So LazyNes is an even lighter library than NESLib, as it has fewer functions. So as a result of that, it obviously takes up less memory, which is a good thing as the NES doesn't have a lot of that. So with a few wrapper functions, the LazyNes library can be tamed, and I hope to provide those going forward. So another good thing with the LazyNes and VBCC is we can also create larger ROM files than the GBDK ones as well, as the minimum size that we can produce is 40k now. So that's full 32k for our actual program now, and the tile graphics are separated into the remaining 8k, which is 2 4k banks. So VBCC means lightweight, and that means fast to build off of. So to work with VBCC, you need to first know how it is set up, or how it sets up the output files for the various computers and consoles that it can be built for. So I'll assume that you've already seen my last video on the VBCC install for Windows users anyway. The Linux, I'll just assume that you've downloaded that yourself. Let me know if you want a video on how to do that. So for myself, I've installed the VBCC library in OPT VBCC 6502. Now if you have a look in here, you'll see that there's two folders here. We have a config and targets. Now these end up being kind of linked together because the config files, they specify a target file. So in here we have the various consoles here, and then the NES configs are pretty much these here. We have the ones we are looking at using are the NROM256V, and then what I've done is I've created another version of that here. So I would advise you to copy this file, create another version of it, call it V2. And then if you open that in a text editor, the bits we are looking at here, so these are basically, this is just configuring the VBCC compiler, telling it how to build against things here. And then the ones you want to look at, these are paths to the target files, which are files which specify how the memory should be laid out in the ROM files or the like tape or disk images for the other computers. So if I get back to here a minute, what we need to do is side by side these a moment. So I'll open another window and we will go to the targets here. And then you'll see in the NES here we have a few different ones here. These are basically for different ROM sizes. However, to work with those you need to know how the sort of banking works. Haven't properly got to grips with that yet. When I do, I'll be sure to make another video on that. So I'll separate these windows here a minute. So this config file is referencing this target file here, and what this specifies here is it tells the linker where the different parts of the code should be organized when you build a program. So you see here we have some RAM area here. The key things to, I'm not going to go into too much detail here, the things that are of immediate interest to ourselves here is this line here basically says whether the ROM cart should be using horizontal mirroring or vertical mirroring. So if it's using horizontal mirroring, then that basically means that it's for vertical scrolling, as the name tables horizontally are duplicated, and then vertically is for horizontal scrolling. And then there's one of these other bytes here which changes whether it's a PAL or an NTSC ROM which is built, I believe. So the you see I've created a duplicate one here which I recommend you do, and then all you're changing in here is just putting this to use horizontal mirroring, and that's the only change. So then you have one setup for, which is the default here, one setup for vertical scrolling and one for horizontal scrolling. And then in the second config file you create, just add a 2 on the end of all of these and then save that. And that just helps with creating the different ROMs. So it means that you'll have one setup for creating a horizontally scrolling project and then the other for a vertically scrolling project. I won't go into any more detail on that here. This is just to you kind of need those to be able to have the horizontal or the vertical options there. So I'll now go over. In fact, let's jump into the actual projects here a moment, so you can see what we're actually making. So I'll assume that you have FCEUX or whatever NES emulator you're using installed. So this one here demonstrates using a load of different size sprites with VBCC LazyNes lib, and then we've got 2 nametables set up for horizontal scrolling here, so we can, using the D-pad, we can scroll left or right here, and then if you go into the nametable viewer, and this is what it's called, vertical mirroring here. There's 4 nametables here, but only 2 of them will actually be used. So we have a very large width screen here, which is using 64 tiles across by 30 tiles down. And then we're able to create a very large width screen there. And we can literally scroll left or right. And then the name table will wrap around either way. Now with some defines here, if you blank out the use X mirroring and then you change, or rather comment out which ROM to build against, which target to build against, and you rebuild that. Now we've got a vertically scrolling one which uses 2 displays high. So you'll see this is using, now we're using horizontal mirroring here. So it's 1 screen wide here by 2 screens high here. So this gives us a tall screen to use for, so if you were making like a vertically scrolling game, this would be the way to go. You would have like one area in focus, and then the other part which is hidden is where you would draw your new sort of tiles to. So we'll put this back to horizontal scrolling there. So to switch over, just comment one out using the hash symbol there, and then in the header file either comment out the define to use mirror X or not. And then all this allows us to do here is it sets up the name table and the attribute table addresses. So I assume you know what the name tables are. They're basically like tile maps in memory where the PPU, which is the picture processing unit, knows what to draw on the screen at any one time. And the attribute table is just a table for which color palette to use for a 16 by 16 pixel area, which is rather a weird way of doing it. Like, you can't sort of set individual 8x8 tile colors, you have to set a 16 by 16 area block. So when we before we can kind of do anything, we need to sort of pass in our sort of character ROM here. So I have some tools for creating that. Unlike GBDK, our character graphics will actually be put into a ROM, which means that you define all of the graphics basically at build time. Before we build the ROM, you have to specify where these where the graphics actually is, and then it also will depend on what you are actually going to be using. If you are using 8x16 sprites, then put the sprites in the first bank here. So the character ROM, there's a region set for the background tiles, and there's a region set for the OAM or sprites, and you need to specify. Well, this here isn't actually 16K. In fact, I can't edit that. Otherwise, I'd have to do something else. So this is actually this is 8K here. The program ROMs. There's two banks there. They are 16K. This is 8K here. There's two 4K character ROMs here. And then before we sort of build everything, we have to set up where the tile graphics will be loaded from. So I have a tool for that, and then this this image here, which I will obviously provide in the links here. So this is, if you split this into a grid of 8x8 tiles here, this image here can basically hold 256 tiles. So when you convert that into a binary file, which I recommend you do, like these here, you just include them in this asm.s file here, and then you must put here section chars, and this just indicates where in the ROM these should be put. This is a section which is defined in the command file, the target file, where it lays out the various memory in a ROM. So the first parts here, so these are all of the sprites which I use in this demo here. They are loaded first, and if we look here, you see we have 2 sharks there, and then I have a number of different sprites here. So these sprites and these sharks, they don't add up to 256 tiles, and that means that I have to add a load of padding, so basically like blank space, to fill out the rest of the tiles. And the reason why I need to provide these, so there's 2 of them here, there's one there and one there, and they basically make sure that these sprite tiles add up to 256, and they are arranged here. And the reason for this is each of these tile ROMs must be 4K in size, and the first load of tiles, it has to be 4K that you pass in here, otherwise you'll end up with the background tiles bleeding into the sprite tiles. So one easy way to do these is to literally use this as a template for your 8x8 characters, and then you can just draw them all out in here, and then use my NES to tile program if you like. It's not compulsory like. So this is slightly different to the one that GBDK was using, and the reason why is because this obviously needs to output in the NES file format now, not the Game Boy format. The layers for the tiles are in a different order for the NES. So all you need to do is drag and drop an image across. So depending on the size you're using, depends whether you actually need to put a size in here or not. So this is going to be an alternative like font part here. If I open that up, so you see here we have the top row set aside for color palettes, and the rest is just tiles here. And then all you do is just drag and drop that across, and then using the left mouse button you can zoom it in, and if you hold down on the middle mouse button, if you have that, then you can move it around so you can see it. And then the options we have here are, we can save it as an assembly file here, so if you click on that, we'll leave that name there. That tells you how many tiles you actually built there. Then if you go in there and open that in a text editor, it's formatted in such a way that you can just copy that and then paste that in here. And then this is the tile data here. So you can either do it this way and literally paste in each tile, so each line here is one tile. Build that again, and then I'll show you that. So it will look exactly the same, and that's because there's no text being drawn. But if you go into the PPU viewer here, you'll see that these actually exist. They are actually there now. So the bottom tile parts have been replaced. You'll see that I split the graphics into regions, as in different image files, and that's to make them easier to work with. And then the other option, if we come back in here again, is you can save it as a binary file. So one thing to notice is it doesn't output any palettes at all. So if we navigate to that there, where is it? Here it is here. So then you just copy that, and then you would just include it right here in your project. And then what you need to do then is in your ASM file is you just write the name of it there. I'll just delete this a minute. So ink bin for include binary, and then utiles.bin. And if we rebuild that, oh, let's put it in the wrong place, which is fine. So now if we look where that is, oh, it hasn't included that. Maybe I put the wrong name. Let's double check. So as you can see there, as it hasn't included that file, there's a gap. Ah, it's because I commented it out. That's fine. So these binary files are literally stacked in order. So this one goes first, and then these are all going in order. They're all picked up by VBCC and then pushed into the character ROM. There you go, we're back in there now. So the way that the sprites work, let's get rid of that one there, put the original back in. So this is like a whole file here, but you can work with like individual areas. Like something, you could like select that part there and then draw like however many tiles wide by high you wanted it, and then in the tile builder just specify the tile sizes. So I'll show you again. I wasn't going to do things on the fly because it potentially breaks things, but I will in this case here. So let's take these out of here. and then we will turn these upside down, and then let's change the colors as well. So let's switch that one for something else. And then we will switch this one for something else temporarily. And then we'll use Shift and R to replace that color. In fact, we want that one there. And then we'll replace this one here. So what we've done here is we've changed the colors, and we've flipped the sprite there, and then we'll save that as Big Shark version 2. Now what we need to do is to rebuild our shark sprite into a binary file, and then we'll switch this one here out and put the new one in. So I'll provide a Windows version of the tool, which is already built into a 32-bit exe file, and I'll also provide the one I'm using here in Linux. The source code I'll provide for that, and the Windows one. So one thing to bear in mind is they use the SDL2 library for windowing, and also the drawing of graphics there. So you will need those to build this. It also uses MinGW32 as well, so if you're going to build this in Visual Studio using standard Windows, then you can not remove the MinGW32 option, and you'll also need to not include the MinGW32 version of SDL as well, so you need to sort of change those if you intend to rebuild it yourself. So let's build this again here. So this is where the width and height comes in handy here. So I recommend that if you're using if this is going to be an constructed of 8x16 sprites, then just put that as 8x16. And then what this will do here is when this is converted, it will convert chunks of this in the correct order for us. And then you also want to make sure that you orientate your tiles here so that it can correctly pick them up. Okay, that looked like it crashed there. Let's try that again. There we go. That's important to note as well, is how many tiles, 8x8 tiles, this thing actually picks up. This is telling us 8x16 though, I believe. So we copy that out now. And then we just change that name there. Rebuild that. And there's our new shark there, like. And if you look here in the tiles for the shark, let's have a look at this here first. So you'll see that the the shark isn't the first sprite tiles here, so it's second. So we have the 16 by 16 sprites first, and then the shark tiles later. So sometimes you might have to play around here with like padding, like I've done here. Another option is you could copy some of these parts into the you could copy parts of those into one of these large like tile templates here and arrange it yourself if you wanted to have it as like one block. Although it's easier just to draw your sort of animations out like this in frames and then just convert them. So that's showing the tiles parts there. So I'll just go over some stuff on the LazyNes lib here. So on the NES, drawing is usually done only during the V-blank, which is when the sort of like raster beam on the TV goes out of the bottom right side of the screen. That's when the V-blank occurs. That's like when the PPU has finished drawing the current TV output frame. So the time that you have is from the PPU going outside the visible frame, and there's like a few like virtual screen lines where it continues to sort of go down, and then once it reaches the bottom of its virtual screen line, then it starts again at the top left. So between the time of the raster going out of the bottom right of the screen and it reaching the bottom of the sort of virtual scan line is the time you have to draw everything. However, you can tell people, you can turn the TV or the display off. The PPU, if you turn the display off, then you can pretty much draw as much as you want. And then you have to turn the display on again for it to start drawing once again. This is how you would draw like a large display in one go. So drawing tiles to name tables. LazyNes provides two lists stroke buffers to allow us to do this, and they are ln push and ln list. So ln push is what you will use when the display is off. You can pretty much just send as much to this as possible. Like you provide like a PPU, a memory address where you want to send stuff to, and then you provide the data for that, and then that kind of gets done instantly, I believe. And then there is another one called ln list. Now this is used while the display is on. It kind of creates like a temporary list of stuff to send to the PPU when it enters the VBlank period. And then this list is emptied each frame update, or it should be, otherwise you'll cause glitches. I will show these in action in a moment, like, and then drawing sprites. On the NES there's an area of RAM which you must set aside for OAM, which is the sprites. That's if you intend to use them. This is normally 256 bytes with 4 bytes used per sprite, and these bytes literally are laid out in like a linear fashion in RAM. So these RAM areas, we won't actually be touching any of them here, but it's laid out in this fashion here. So the bytes are like Y position first, then the tile ID for the sprite. There's then an attribute byte. So what we can do with the NES bytes is we can actually flip them on the X and Y axis to mirror the tile graphics, or we can specify a byte to draw them behind the background. And then finally there is the X position of the sprite. So LazyNes has like handles this sort of for us here. It has like another list for add-in sprites, and the way that this list is set up allows for like large meta sprites to be created, and this organizes the sprites in a buffer for us and puts them in the OAM area, which is then updated every VBlank. So you have to send this list every VBlank, and only the sprites which are in there will actually be drawn. So if you don't include a sprite in there, then it will be hidden on the next update. So these buffers that we must pass, they are laid out in this sort of fashion here. We have the X offset from the X position here. What we'll do is I'll side by side these a moment so it kind of makes some sense to what I'm talking about. So if I bring up the Sprite Manager code here, so this is one command here for drawing a 16 by 16 sprite. We have a local array in here, which is the buffer we pass to ln add sprite, which is the LazyNes function. This creates like a nice wrapper for us here. So this buffer is laid out to draw two sprites, which are 8 by 16 in size, and these bytes have 4 bytes per sprite, and they are, so the first one here is the X offset from the X position. So what that means is when we use the ln add sprite, we pass in a buffer, and then we pass in the horizontal and vertical positions we want to draw that sprite at. The first 2 bytes are an offset from this X and Y position, which moves to the right or down from the X and Y position here. So this is useful for constructing larger sprites. If I bring back the picture of the shark here, and then I set this grid up to 8 by 16. So each of these 8 by 16 tile parts here can be thought of as one sprite. So this would be sprite 0, this would be sprite 1. Now this here, you follow these numbers here, this would be 8 across by 0 down as the offset. This would be 16 by 0 as the offset, 24 by 0 and 32 by 0, and then the vertical part would be 0 by 16 for the next one, then 8 by 16 and so on to draw the shark, which you can see here. This is the arrangement here. So see this 8 by 0 and then 16 by 0. This is in hexadecimal here. It just makes it easier to lay these numbers out here. And then these buffers just allow for the exact sort of size of these sprites here. And then when you get the end, you must signal an end byte, which is 128 or 80 in hexadecimal here. And then we set some parts of this buffer here. For example, this here, the third byte is the tile ID, and then the end byte is the attribute ID. And then these just repeat every 4 bytes pretty much. And by setting these up, this allows us to construct any size sprite we want, obviously as long as the NES can actually draw that. And then yeah, each buffer should end with x80 there. So that's all I will go through for the LazyNes lib here. These are the key things to know: the ln push, ln list, when to use these, and then the sprite list, how that works. So let's get back into some of the code now. I'll tell you how some of this works and why you might want to use this here. So the power of all this will be in the header files here. So I'll jump into the utilities structure we have here first, and I'll go over some of the things here. So I have some wrappers or wrapper functions around what I call the draw list. So if we come down here, so this draw list, this wraps around the ln list function, which is the one you use to draw tiles while the display is on. So it's limited in size. You can only draw about 32 tiles to that. And what these functions here allow us to do is to write meaningful stuff to that while the screen is on. And then I've also got some of similar functions I used in GBDK here, and then I've added 2 other functions here for display on. So if we check that out here, so that's just some other important stuff with the LazyNes lib as well. Is lots of stuff is just done via these lists, which is basically like the most simplest way you can pass multiple bytes. And then if you you look in the header file with LazyNes, it tells you what these things actually do here. There's not a lot in here. These are some of the parameters we can pass to ln list. So one thing to note, when you send like tile data to the PPU, you can have it either write tiles horizontally or write tiles going vertically. So if you think of like you scrolling horizontally, you might want to set this to vertical before you draw a line of tiles going vertically down the screen. And then if you were scrolling vertically, then obviously this would be set to horizontal, and it would draw a strip of tiles going horizontally across the screen. So another thing to note here is the draw list. This needs to be updated before the screen goes into VBlank, which is what this does here. So this flushes everything out when you turn the display on, as there is a fixed size in there of 128 bytes. So before you use it, you should always make sure that it's emptied. And then during VSync, this draw list is sent to the in-memory list, which is drawn to the PPU automatically for us when VBlank occurs. So some useful things here. So if you are familiar with what the attribute table actually is, the way that the palettes are kind of stored is very odd. It kind of stores 4 tile parts in 1 byte. It kind of is a simple sort of a compression format. Where it basically, in 1 byte, it packs 4 tile parts. And this is what these kind of help with here. I won't go into any more detail on these here. If you check out the NES lib wiki, which I'm sure you already have, then it will have more sort of information on everything here. Sure, there's some stuff in here about the attribute table, as I'm sure this is where I've got it from. Not necessarily this here, but these are some useful functions here which I have. So if you need to work with the name tables yourself, these macros here will automatically calculate the first name table for you. So I have some global variables which I use for most stuff here. So we have like a number, a buffer there for printing numbers, which I haven't put the functions in here, so don't worry about that for now. Like this video is just to kind of get you sort of started. The follow-up videos will be actually making a game. So these are some useful functions here. We have draw 1 tile, or you can draw like a double height tile, which is 8 by 16, or this will draw a 16 by 16 block. And then I have some other commands here which will draw a 16 by 16 block, and you specify the palette ID, and then it will actually go in and put the data into attribute memory and the tile. But notice that these values here are in 16 by 16 tile blocks. and then I have a similar one here for 32 by 32 block. And then what this command here does is it will put a byte into color memory, as in the attribute. As you see here, what it's actually doing. So you would have to do this with the display off. And then we have some more color tile put functions here. This will print a message out on the screen, and this will print one centered. So some of these you should use with only the display off, and others with the display on. So normally what you'll be doing with these sort of streaming commands here is, if you wanted to immediately sort of send a load of data to the PPU, first off you would call draw list begin. You would then put in the address you want to send stuff to, and then the fill type. So this was you'd put LFHOR or LFVER here, as it's going to be using the LN list in the background here. This is what this does. These create a load of wrapper functions around using the LN list. And the reason for it is you call this command once and it expects this data buffer or array that you pass in to be arranged in addresses and field types and bytes, and then the list you must end with 255. What these commands here do is they do all that for you. Lots of the time you probably will not touch this directly, which is why I've put this in here. Some of them, if you look at some of these commands here, you'll see that what it does is I have like a global variable in here which is monitoring whether the display is on or off, and also what screen ID you are actually using as well. As there's always two name tables active, so if you have your screen set up to scroll horizontally, then you obviously have two screens wide. But the way the tiles are organized, if I bring this up a minute, try and show you here. So you see here we have two grids of 32 by 15. You can think of these as being miniature name tables. So to draw anything on this one here, it's always going to be between 0 and 31 going across, and 0 to 30 going down. But to draw on the second name table, you can't just directly, these aren't linked together, so you can't basically plot things going straight across normally. You have to kind of split them into separate regions and then kind of work out which region you are working in. So to simplify that, what I did was I created the screen ID here. You change that between 0 and 1, and then it will draw on either name table A or name table B. So in this case, name table A would be the first one, name table B would be the bottom one. If this screen is set to vertical scrolling, then they're now arranged like this, with one on top and one on the bottom. Now the NES has the size for 4 name tables. The PPU has name tables for 4 in its memory. So some of these are mirrored or not used basically. So if you are in horizontal mirroring, then these 2 name tables will be in use, and these will just be copies of these. But to actually send tiles to these, you need to know the actual addresses in memory of these, and they are kind of laid out like this. You have the first name table there, the second one there, then the third, then the fourth, which is what you can see here. All of the name tables have different addresses. Same with the attribute tables. These are arranged after the name tables. So depending on which mirroring mode you have, the name table addresses are different, which is what's going on here. We have our setup name table B to be either so this would be in the horizontal scrolling. The if X mirroring is set to 1 here, then we are using these 2 top name tables here. Otherwise, we're using name table 0 and name table 2, which is this here. So this is name table 0, that's name table 1, that's 2, and that's 3. So you see that we're never actually using 3. We're either going to be using 0 and 2 or 0 and 1. And then by using the screen ID, you can specify which screen you actually want to plot tiles to. Screen 0 or screen 1, and then this will work out which name table you should actually be using here in the tile command. And then you'll see there's another bit here for if you're doing this with display on, then we send the details to the draw list. So what the ln push actually takes here is it takes an address as a 16-bit number, how many tiles or bytes you're sending to it, and then usually it requires a pointer to that data where it then copies a byte from there, or however many you specify. So this is just wrapping that around, and then that's what all of these other these other commands are doing here. They're just building on the previous. So if you draw all the tiles while the screen is on, there's a chance you'll get an error if you draw too many. As I have an error function here, so you can use this for debugging, which is what I use it for as well. What this will do here is it will turn the display off, and then it will clear the first row with tile 0, and then it will print out your error message. So if you need to kind of try and error trap something, you can use this as well. You could use it like a breakpoint. So another thing I've not covered as well, which I'll cover now, is the graphics converter does not use color palettes at all. It doesn't give you those. You'll have to work those out yourself. So what I will give you for that, which is what I use, is, where are we? This is the one here. So the colors vary depending on what NES type you have, but this is like a rough guide here. So I've scaled this up. The colors here, they do not match the numbers here, but these numbers are what the colors should be you use in your color palettes. So when you create your images, you'll be let's bring up one of these as an example a minute. So I would say to create colors which are aligned to numbers of 8 here. So you see that color there, 248 by 160, mirrors this one here in the NES. So I would, as you're working with these, make a list of the colors like this here. So then we have 3 colors here, 27, 17 and 7, which are these colors here. So these colors here, this is like a palette, I believe, from FCEUX, which I created a while ago, to give me a kind of idea how things will actually look. The loads of different NESs, they have slightly different color palettes, whether it's PAL or NTSC or some of the NES clones. So I didn't bother trying to hard code color detection, which would be a pain. Rather, the way you do it is just create like a palette array like this. Usually I set aside 1 color for like the background, and then just use 3 bytes for the other palettes. And then use where are we a minute? And then just use that command there, set background color, or depending on whether you want to use any of my functions or not, or just use the direct LazyNes things here. So you can either notice here the display off and the display on pairs. So the whole screen is pretty much drawn here using this sort of a map here of tiles. while the display is actually off, which is the way you kind of do it. You sort of draw the majority of things with the display off and then switch the display back on to display that, and then update things only a few at a time while the display is actually on. Don't have to worry about the sprites while the display is on. You can carry on with them, but if you want to draw any tiles while the display is on, then you would need to use the LNList functions, which I kind of wrap around as the draw list stuff here. So you see here I have a load of like constant variables here. So I use this here as like a 8-bit pointer. These are some sort of global variables just for like using in various loops. And then I use this as like a general purpose random number generator. And then these here, I won't bother going into any detail on these. These basically allow you to create like a rectangle collision and check for that. Kind of this isn't really in scope for this video here. So one thing that I do have here is this is like a virtual color table. So this is like a version of the attribute table which we can back up. And the reason why I create this is so we can update things on the fly. Whereas once it's sent to the PPU, there's obviously no way to easily get back the data there. And the this command here, color part, this handles plotting individual 16 by 16 pixel areas for us. What this does is it sends and works with what's already in the color table, and then when you're finished you then use the color send, and then that will either use ln push to send 64 bytes to the relevant attribute table depending on what screen you've got active, or if the display is on then it will use the draw list. So one thing to note is the draw list, if you're sending that, I've set it to 128 bytes here. So if you're drawing loads of tiles and you're dynamically updating the attribute table, this could cause a memory overrun and an error there. So let's think, is there anything else? What I'll say is just have a play around with loads of this. And then the code is here for you to have a look at and see what's actually going on here. These are things that I use myself. So one thing to bear in mind as well is only one full attribute table can be sort of done at a time. So if you look at what was actually happening to draw this, so to draw these mini levels, if you like, what we have here is depending on which one, whether we're using. So this one here, if this is on, then it's like a horizontal. If this is set to 1, then it's horizontal scrolling. If it's off, then it's using this map here for vertical scrolling. And then these just indicate which tile to draw. So another thing to note as well is these tile regions here are 16 by 16 block numbers here, and they refer to, if you look in the graphics define thing I have here, this sets out where exactly in the PPU these tiles actually live in the tile bank. So this if I open this up again here, it helps if I have the actual ROM. So if I open this up again here, we go into the PPU viewer here, you'll see here that the star tile here, the background tiles basically start at A0, which is 160, which is here. So I literally, after I sort of built all these, I kind of create like a list of where they sort of start. So you'll see the ball starts at A4, and this is just adding 4 to the previous one here. These just create like a list of where everything is defined to draw these. So note that these are all sort of one after the other. So to draw like a 16 by 16 tile, they all should be arranged going from top left to bottom right in the end. That's the same with the 32 by 32 tiles as well. So there's one here, there's like enumerations here for the sprites. And then I have defines for the background palettes as well. Just so I have an easy reference to know where the graphics is for drawing, which is what this is doing here. So if I open up, I'll show you how these were sort of constructed. So you might want to, you can either do this by hand to draw your levels. So this is a one tile map here, and this is another tile map. If it's divided into 16 by 16 blocks, that is, you can think of it as like this is like the left screen, this is the right screen, and each of these colors represents a different tile type. So these first 4 here represent these 4 32 by 32 blocks, and then these green pixels here represent each of these 16 by 16 background blocks here. Notice there is an empty space around the 32 by 32 ones here. And that's because they take up 4 16 by 16 tiles. So the options you have for doing that is you can either do this by hand like this, or you can look for the DS to tile program, and then set that to a 256 color bitmap, and then set that to a 16 by 16 area. And then just drag that across, and then you save that. Ah, it's because it's too big. Okay. Yeah, of course it is. There you go. As you see here, I've already sort of built these horizontal map or vertical map. And then this just allows you to easily create another level. So if I create another one here to show you. And then what we'll do to make it obvious here is we will have all of these 32 by 32 blocks here, create like a huge wall region on this one side. And then I'll just use one of these tiles here to do this. So note you'll need to do it as 16 by 15. As that is the size of one of the screens. I think that's how I did it the other day. We'll find out in a minute. This is the problem potentially when doing things live, as I don't want to make another video of this. So this is the horizontal map here. Cut that out. And then I'll just paste that in here for safekeeping. Take the new one in. Yep, that's right, there you go. Now we've got VBCC there. And then we have the wall of 32 by 32 blocks there. If you view that in the name table viewer there, you can see the full region here. We're basically just plotting the tiles in there. Get rid of that there. And then I'll bring back the other one there. So I think I've gone over the utility functions there. Again, have a play around and get to grips with using the LazyNes library there. So I'll jump more back into the code here a minute, what's going on. So these block put commands here, what this is actually doing is the display is off here. Before we do anything, we fill the color table with 0, so it basically blanks that out. And then what this is doing here is this is kind of drawing two name tables in one go. It's iterating over it twice. And this draw map function here is taking one of these maps here, as it's using the if defs to basically only include one of these depending on if this is defined or not. And then as the name tables are split into 2, I'll include the this palette image as well, as I'm sure that will be very useful. Won't talk about sound in this video because obviously it will just run for ages else. So what this does here is we're checking for the block types. Where have I defined that? It must be in here. Yeah, here we go. I've created like a define for the tile types in the map. And then we're setting individual colors depending on what the tile type is. And you'll see here that some of these colors are random. As in, this is being iterated over every tile plotted. So I don't totally know what color these will be. Some of them I didn't sort of specify a color for. So this kind of draws one name table first and then draws the second, as both of them will be laid out in 16 by 15 tile parts. This function can draw both of them. And then these are just some variables here to handle moving the sprites around. This is an essential setup here as well. So this is sending this bit flag here to the PPU controller. Again, there's wiki for this option here. You will want to have a look at some of the things you can do, like, so you have to tell the NES via this bit flag here that you want to use 8 by 16 sprites, and then you have to tell it which bank the background tiles are to be read from. So it's either going to be character bank 1 or character bank 0. In our case, it's using character bank 0, as you can see in here all of the sprite tiles being drawn first, so they'll be sent to character bank 0, and then the background tiles will be sent to character bank 1. And then we the displays off here, set the what background color we want, which is in the background palettes array here. So you see the first one is the background color, and then everything's set into groups of 3 here. and then we use this 8-bit pointer here to point to the second byte in the array here, and then that starts at the main sort of palettes, and then we use the set tile palette command here, which wraps around another ln push command or a draw list command. And then I'm just peeking a random memory location. This will probably do nothing at all in an emulator. This is like the address for like a RAM address on the NES, which could potentially be random, and I'm just dividing that then by 16 here using the shift right by 4. I then clear the screen, as I don't know whether there will be any sort of garbage in memory at all. Again, doesn't really matter on an emulator because it's probably all going to be cleared up for you, whereas on a real machine the bytes could be anything at turn on, you know. Then set up sprite palettes. Again, this uses ln push or the draw list to do that. So this is drawing all 4 of them here. So you can you pass the start palette number you want to use, and then this just sets this general word unsigned U16 unsigned word, sorry, unsigned short to the memory address to use where the sprite palettes are, and then it either pushes 3 bytes using ln push, or it sends those 3 bytes to the draw list for you automatically. And then we draw the map here as above, set the screen to 0, and then turn the display on, and then this just draws the various sprites here. So we've got if I bring up Sprite Manager here, so we're side by side. So this will draw 1 sprite here, and then this will draw a 16 by 16 sprite, and then this one here will allow you to horizontally flip a sprite as well, and also change the palette it uses. I don't know if you noticed it or not. Let's open it back up again. So this one here is, although it's really fast, it's cycling through all the sprite palettes. I should probably slow that down. I'll allow you to do that. I don't want to spend any more time playing around with this. And then all this is doing here, there's a separate one for the shark. As it uses a load of sprites. So one thing to note here is depending on the size of your sprites here, you just need to vary the size of the buffer. So if you had like a Mario sprite or something, you could have like 16 by 32 sprite. So then you would just change the buffer size here, and then you would need to change where the various attributes and tile IDs were into these buffer arrays here. So most of these you can just think of it as like a toolbox. You wouldn't include everything all the time in all your projects. You would literally just I don't know, this one here you probably use all the time, same as this one here, but the others would you probably wouldn't use all the time. They'd just be if you were using this size sprite, you know. And then this is just flipping stuff around, and then we just have a timer here to say when to flip stuff. And then this here handles the scrolling with the D-pad. If it's in scroll horizontal mode, then we check the left and right keys, and then we send the scroll value using ln scroll to just the horizontal number. If you check that out there, it has more details. So you'll see here the X range should only be between 0 and 511, and then the vertical range should only be between 0 and 479. And then at the end we call vsync, and then what that does is that will empty our draw list buffer if there's anything in it. So I think that's it for this overview of VBCC. Hopefully you'll find this useful. I'm not sure what game type I'm going to do next, but there will be a game coding series coming up using VBCC on the NES, so stay tuned for that. Any questions, leave them in the comments below. I will leave links to the project files and also the tile builder below. The tile builder again will be split between Windows and Linux, and then check out one of the DS videos to find the DS to tile program if you want to use that. So that's it for this video. I will catch you in the next. Thanks for watching.